Hi, this is Amit Kirti here. In this video, I would like to talk about Quicksort algorithm. So the items for discussion are Quicksort Introduction, Quicksort Example, the Quicksort algorithm itself, and then we will look at Quicksort algorithm with an example to illustrate the algorithm. Now, Quicksort algorithm is actually a divide and conquer method of sorting elements. Quicksort is one of the most efficient sorting algorithms which has a time complexity of the order of theta of n log n. The Quicksort was actually invented by Sir Charles Anthony Richard Hoare in 1960. If I were to summarize Quicksort in probably a couple of sentences, I can say that Quicksort basically selects a pivot and then it tries to place the pivot in its place, and then it tries to recursively sort the left half and the right half of the pivot element. So we'll see more of it when we see an example and the algorithm itself. Now let's assume that I have a set of numbers as shown here, and I would like to sort these set of numbers. So the Quicksort algorithm first places a pivot on one of the elements. Let's say we place a pivot on the first element. Then what we do is we try to place two indices which will go through the list. So there will be two indices I and j. So I will start from the left hand side and j will start from the right hand side. Now the algorithm proceeds as follows. Now I will keep on moving ahead till it reaches an element which is greater than the pivot. So if I points to an element which is less than pivot, it will just keep moving ahead. So in this case, we actually see that I points to an element 3 which is less than pivot. So I will simply keep moving ahead. So we compare 5 and 3 and we see that 3 is less than 5, that is the value that I points to is less than pivot. So I will keep moving ahead. So next we try to compare 5 and 1, and since 1 again is less than 5, pivot has to move ahead, the index for I moves ahead and points to the next element, that is 9. Now since 9 happens to be greater than 5, our condition does not satisfy, so I just stops at this point. Now j has to start moving towards the left. Now the condition for j is that it should keep moving as long as it points to an element which is greater than the pivot. If j starts pointing to an element which is less than the pivot, it has to stop at that point. Now you see that j points to an element whose value is 7, and since it is greater than the pivot, it will actually these are the previous steps, so we actually stop at this point, and then j, we start with j. So j actually is pointing to an element which is greater than the pivot, so j moves ahead. Now j points to the element 4, and since the element that j points to is less than the pivot, we actually have to stop here. So this element is greater, so we are going to stop at this point, and then what we have to do is we have to actually go ahead and swap the elements that I and j point to. So the elements 4 and 9 get swapped with each other. Now at this point I will start continuing further and start pointing to the next element, which happens to be 8 in our case. So now again, as I was saying, I has to stop at a point where it points to an element which is greater than pivot. So here we see that I points to 8, and since 8 is greater than pivot, it has to stop at this point. Now once I stops, j resumes its journey towards the left side. So j will continue ahead and then point to the next element, and it stops if it is pointing to element which is less than pivot. In our case, j is pointing to the element 2, and since it is less than the pivot, it stops at this point. So logically the next step will be that I and j swap with each other. So the element 8 and 2 get swapped as 2 and 8, and then I continues its journey and to point to the next element, and as we were saying, I will stop when its value is greater than pivot. So here we see that I points to 8, which is more than pivot. So I stops at this point. And j resumes its journey towards left hand side. So j will resume its journey towards left hand side and it starts pointing to the element 2. Now, since the condition for j is that j should stop when its value is less than pivot, j stops at this point. Now the next logical step is, since I and j have crossed each other, the elements pivot and the j have to actually swap with each other. So we have swapped 5 and 2 and we see that the element 5 has reached in its place. So pivot was pointing to the element 5 and what we have done is we have moved 5 to its place. Now let's try to look at what we observe in this set of numbers. We see that the pivot element 5 has reached its place, and if we carefully observe the left hand side of 5, we have an unsorted list of numbers, but they are all less than 5. And the elements on the right hand side again are unsorted, but the point to note is they are all greater than 5. So what this effectively means is that whatever we do with the left hand side or right hand side, 5 will remain at its position and we have to recursively sort this left side and right side. So basically 5 is in its place and we have to sort the corresponding left and right hand side of this element 5. So we will rewrite the list of numbers as below. So 5 indicates it is in its position. So we have to start with recursive left half. So what we do is pivot starts pointing to the first element. The indices point to their corresponding elements, that is I points to the element after pivot and j points to the end of the list. So ideally I should start going towards right direction and j should start going towards left. So right now we will start with I. So what we do is, as before, I should keep moving ahead till it reaches a point where it points to an element which is greater than pivot. So now I points to element 3, which is actually greater than pivot, so it actually stops at this point. So I has stopped at its point and j resumes its journey. Now as we were saying, the condition for j is j should keep moving towards the left as long as it points to element which is greater than pivot. If it encounters an element which is less than pivot, only then it should stop. Now right now j points to the element 4 and the element 4 is greater than pivot, so ideally j should actually move ahead. So j moves ahead and starts pointing to the next element. So right now j points to the element 1, and as we were saying, j should stop when it points to an element which is less than pivot, and in this case we see that j points to element 1 which is less than pivot, so j actually stops at this point. So now once j stops, we have to swap the elements that I and j point to. So 1 and 3 will swap with each other, and at this point I continues its journey from here. So for I, it has to continue as long as it points to an element which is less than pivot. So since it points to an element 1 which is less than pivot, I moves ahead. Now I is pointing to the element 3 and we said I will stop when it points to an element which is greater than pivot. So I is pointing to 3 and it's greater than pivot. So I stops at this point and j resumes its journey. So j now is pointing to the element 1 and the condition for j is that it should stop when it points to an element which is less than pivot. So right now j is pointing to an element which is less than pivot, so it stops at this point. So once it stops at this point, what we see is that j and I have crossed each other. So ideally now we should swap the pivot and the element that j points to. So both the elements get swapped and 2 is in its position. So what we have effectively done is we have taken the left half, which actually consisted of the elements 2, 3, 1 and 4. We pointed the pivot to the element 2 and we tried to use two indices I and j such that we can place 2 in its proper position. So now what we see is that 2 is in its position, and we have some elements to the left which are less than 2 and some elements to the right which are greater than 2. So what we have to do now is to recursively go to the left of 2 and right of 2 and try to sort the left and right part of 2. So this is our condition right now, where 2 is in its position and we need to sort the left and right. So let's try to clean this up so that it looks much better. So what we see here is that we go to the left of 2, and to the left of 2 we just have one element, so we really don't have to do anything, because we really cannot sort just a single element. So the element 1 is actually in its place. So 1 has been sorted. So we have gone to the left of 2 and sorted just the one element. So we are actually left with the right half of 2 that needs to be sorted. So we just clean the list. So we have the left half of 2 is sorted, and we will try to sort the right half of 2. Now the right half of 2 has 2 elements, that is 3 and 4. So we will put the pivot on the first element, that happens to be 3, and we will place the 2 indices I and j on top of the leftover element, which happens to be just 4. So as per the rule, I should keep on moving as long as it points to an element which is greater than 4. So since I points to an element which is greater than 4, I actually stops at this point, since it cannot move any further. Now the condition for j is that it should keep moving towards the left as long as it points to an element which is greater than the pivot, and it should stop when it points to an element which is less than pivot. Now since j is pointing to the element 4, which is greater than pivot, the condition satisfies, so j moves ahead. Now j now points to the element 3, and since the element is not greater than 3 or the pivot, j stops at this point. So once j stops at this point, we see that j and I have crossed each other, which effectively means we should stop at this point and swap the pivot element and a of j. Since both are pointing to the same element, we are actually done with this particular element being in its place. So we have placed 3 in its position. Once we have placed 3 in its position, we have to go to the left half of 3 and right half of 3. So first, when we try to go to the left half of 3, there are no elements on the left half of 3. So what we are left with is we need to try and go to the right half of 3. So there are no more elements to the left of 3. So we are more or less done with the left of 3, and we have to go to the right of 3. So we have placed a pivot on the element 4, and we also place the indices I and j. Since pivot I and j, everything point to just one element and there is nothing to sort, so the element 4 is in its position. So once we have placed 4 in its position, we are done with the left half of 3, which had nothing, and right half of 3, which had just 4. So we have to return back in the recursion, and we go to the element 2. So we are done with the left half of 2. We are done with the right half of 2, which contains just 2 elements, 3 and 4, and both the elements are sorted. So we are done with the left and right half of 2. So we have to recursively go back to the parent of 2, and the parent of 2 happens to be 5. So what we have done is we are done with the complete left half of 5. So you can see that the elements are sorted, that is 1, 2, 3, 4 and 5. So now what we are left with is the right half of 2, the right half of 5, which has 3 elements, that is 8, 9 and 7. So now what we do is we place a pivot onto the first element, that happens to be 8, and then we place the indices I and j such that I points to the element on the left side, left end, and j points to the element on the right end. So now again we start the quicksort by checking the logic as usual. So I has to keep moving as long as it gets an element which is less than the pivot, and it has to stop when it encounters a value which is greater than pivot. So we see that I right now is pointing to a value which is greater than pivot. So we are actually I cannot go for, further, so I stops at this point. Now the responsibility is on J, so J has to move towards the left as long as it points to an element which is greater than pivot, and it has to stop if it encounters a value which is less than the pivot. So we see here that J is pointing to an element 7 which happens to be less than the pivot, so J has no option but to stop at this point. So once both I and J have stopped, they have to swap the elements that they are pointing to. So the elements 9 and 7 get swapped as 7 and 9. So once we swap the elements, I continues its journey, and since it is pointing to an element which is less than pivot right now, so I continues further to the next element. Now I points to the element 9 which is greater than pivot, so it has to stop at this point. So I cannot continue further, so I stops. Now J resumes its journey because it is pointing to an element which is greater than pivot, so J continues further and then moves to the next element. Now since J is pointing to an element which is less than pivot, so J cannot continue further and it has stopped. So what we need to do here right now is that J and I have crossed, which effectively means that we have reached the end of this process for this elements. So we are actually supposed to swap the elements 7 and 8, that is the element P and A of J. So once we swap the element, the pivot element 8 has reached its position. So we actually clear it off, so I am writing back the numbers here. So 8 has reached its position. So once 8 reaches its position, we have to go to the left half of 8 and try to sort, and then go to the right half of 8. Now the left half of 8 is just the element 7, so pivot points to the element 7 and the indices I and J point to the element 7. Now since it is just one element and there is nothing much we can do, we just say that we are done with sorting of 7. So once we are done with the left half of 8, we go to the right half of 8 and we point the pivot to the element 9, which is the only element on the right half, and the indices I and J also point to the same element. Since there is nothing much to sort, since it is just a single element, we are done with this element as well. So basically we are done with the left half of 8 and right half of 8. So we will go back to 8's parent, which happens to be 5, and for 5 we are done with the left half of 5 and right half of 5. So basically we are done with all the elements of sorting of all the elements. So now let's try to look at the Quicksort algorithm, and then we will also try to analyze the Quicksort algorithm using the same example that we saw. So this is the first step of Quicksort algorithm, where it takes an array of numbers. So in our case, let's try to put these numbers as we see here. So it says the L is the lower index, that is it points to the element 5, and R is the higher index which points to the element 7. So we check if L is less than R. Yes, L is less than R. L is here and R is here. So what we have to do is we have to partition this into two parts. So we call a partition function whose output will be a partition of this array, where the pivot would be in its appropriate position and the whole array would be divided into two parts. So what we do is we call the partition function first, and then the partition function says the pivot should be A of L, that is the leftmost element. So we will try to place a pivot on the leftmost element. Then it says I should point to L, that is it should point to an element which is same as a pivot element, and J should be outside the array. So I starts to the leftmost value and J starts outside the array. So once we do that, the algorithm says repeat this until we encounter a scenario where I crosses J. Since I has not crossed J, we enter here and it says keep incrementing I as long as you reach, as long as you keep finding a value which is less than P. So if you find A of I as greater than p, then stop incrementing I. So first step is increment I and then check whether a of I is greater than p. So 3, since it is less than 5, I will move ahead. So keep incrementing I till you reach a scenario where a of I exceeds pivot. So 1 does not exceed pivot, so I will still keep moving ahead. Now we have reached a scenario where a of I, that is 9, exceeds the pivot element. So we will stop incrementing I and we will go to j. So what does it say here? It says that keep decrementing j as long as this condition does not hold good. Once you hit this condition, then stop incrementing j. That is, as long as a of j is greater than pivot, keep decrementing j. So first we decrement j and we check whether a of j is less than p. Since a of j is not less than p, j moves ahead. So we are decrementing j again. And right now we have hit a scenario where a of j is less than p. So I kept moving to the right hand side and it stopped when this condition got satisfied, and j kept on moving and it stopped when this condition got satisfied. So both I and j have stopped moving. Then we have to swap a of I and a of j. So we swap 9 and 4 to get 4 and 9. And then we check whether we have reached this condition. Has I crossed j? So I has not crossed j. So we will go up again, and then again I increments further, and then we check whether we have hit this scenario. Does a of I is a of I greater than pivot? A of I is 8, which happens to be greater than pivot. So I stops at this point. Next we continue with j, that is we decrement j, and then we check whether j points to an element which is less than pivot. Since j points to an element which is less than pivot, we stop decrementing j and we come out of this repeat loop as well. So once we come out of this repeat loop, we have to swap a of I and a of j. So 8 and 2 needs to be swapped. So they get swapped as 2 and 8. So again, once we swap, we check, have we reached a condition where I is greater than j? Again, I is not greater than j. So we will go up in the repeat loop and again increment I. Once we increment I, we check, have we reached a scenario where a of I is greater than the pivot? So a of I is 8, and since it is greater than pivot, we will stop incrementing I and then go and decrement j first. So once we decrement j, we check whether a of j is less than pivot. So here we see that a of j is 2, which is less than pivot. So we stop decrementing j as well. So once we stop decrementing j, by default we go ahead and swap the elements. So 2 and 8 have got swapped as 8 and 2. But then when we see, have we reached a scenario where I is greater than j? So here you will see that I and j have crossed each other. So I is greater than j. So we have actually hit this scenario. So what we do is we come out of this repeat loop, and by mistake we had swapped the elements 2 and 8. So what we do is we swap back the elements and we get back 2 and 8. So once we swap back the elements, we go ahead and do this final step, that is swap elements p and a of j. So pivot, that is 5, and a of j 2, they get swapped with each other. So now you see that 2 has come here and 5 has gone here. So the element 5 has actually reached a position where it has been sorted. So what we do is we return index to the element 5, that is j is pointing to the pivot element. So from partition function we return back to quicksort and we return, so s contains the pivot elements index, that is the index of 5. So what we have done is during the partition process, 5 has reached its position and the elements on the left half of 5 are all less than 5 and the elements on the right half of 5 are all greater than 5. So next what we do is we recursively call quicksort inside quicksort, and this time we pass only the left half of the array, that is the elements 2, 3, 1 and 4. So once we call the quicksort 2, 3, 1 and 4, The quicksort algorithm gets called here. So I'm rewriting the numbers just for the sake of clarity. So here we have the left half and we start doing a partition on the left half. So what does the algorithm say? Pivot should always point to A of L. So in this case, we have A of L as this element. So pivot actually points to this element, and I should point again to L. So I starts outside the range, and J also points to R plus 1. So J also starts outside the range. So I starts with same element as pivot, and J starts outside the area of 2, 3, 1, 4. So J points to the element 5, though it is not of any help right now. So once I and J have been initialized, we enter into this repeat until loop, and then the first step that we do is increment I. So once we increment I, we check whether we have hit this condition. Does A of I hit a condition where it is greater than the pivot? Here we see that A of I is 3, which is greater than pivot. So I stops at this point. Next, J starts decrementing. So first J has to decrement first. So now it is pointing to the last element on the left half. So A of J happens to be 4. So we check whether we have hit a condition where A of J is less than pivot. So since A of J is greater than pivot, so J can continue further, and so we decrement J again, and then we check whether A of J is less than pivot. Now A of J is 1, and since 1 is less than pivot, we have actually hit a condition where we have to stop executing this while loop, repeat loop for J as well. So we have stopped for I, we have stopped for J. The next logical step is to swap A of I and A of J. So we swap 3 and 1 and we get 1 and 3. So once we swap, we check whether I has crossed J. Now I has not crossed J yet, so we will again continue in the same repeat until loop, and then first we go ahead and increment I. So I moves ahead and we check whether we have hit a scenario where A of I is greater than pivot. So we actually see that A of I is greater than pivot. So I stops at this point and we go for J index, and first we decrement J, and J points to this element, and we check whether we have hit a scenario where A of J is less than pivot. So we actually see that we have hit a scenario where A of J is less than pivot. So J also stops at this point, and we go and swap A of I and A of J. So this is actually a mistake because this was not really required. So once we do a swap, we will actually see that I and J have crossed, and we will undo the last swap here. So we will get back 1 and 3. So once we undo the swap, then the last step here is actually to go and swap the element pointed to by P pivot and the element A of J. So we will actually go and swap them. So for 2, 1 have become 1 and 2. So the element right now 2 is actually sorted. So the element we have colored it here. So the element 2 has got sorted in its position. So we will return the index of element 2 back to Quicksort. So again we can see that the same so the 2 has been sorted in its place, and the left half of 2 is unsorted and the right half of 2 is still unsorted. So what we do is we go back here. So once we go back, the partition is done. So we will call Quicksort on A of L and S minus 1. So in this case, S points to the element 2. So we are recursively calling the left half of 2, which happens to be the element 1. So what we do is, once we call Quicksort on 1, there are no elements to be sorted. So once Quicksort of 1 was called, since L is less than R fails, so there is just one element. So we have nothing much to do here. So then we go to the right half of 2, which happens to be the 2 elements. So we come out of this and go into Quicksort with the right half of 2, which has 4 and 3. So what we do here is we have to sort 4 and 3. So we go into the partition function where pivot points to the element 4, and then L and R are assigned again as below. So L will point to the element on the other side of the pivot, on the other side of the list, that is, it points to the element 4, and J is outside the list. So I, for I, it has to continue its journey as long as first it will increment I, and then we will check whether A of I is greater than pivot. So once we do this, we check, we see that this condition fails, so j comes in, j gets decremented, and then we check whether A of j is less than pivot. So A of j 3 is less than pivot, the condition gets satisfied. So what we do is we move ahead, and then j and I cross each other. So once j and I cross each other, we actually go ahead and we swap these elements as 3 and 4. So the elements have got swapped as 3 and 4, and the element 3 has got sorted. So once 3 has got sorted, then we actually return back index of 3 to quicksort. So we have the elements 1, 2 and 3, and once we return the index of 3, we try to quicksort the left half of 3, and there are no elements that are left on the left half of 3. So the left half of 3 is empty, so we have nothing much to do. So we have to go to the right half of 3, which has just the element 4. So once we call quicksort on the right half of 3, so once we do that, we call quicksort on just one element, and L is less than R fails in this case. So what we do is we don't do anything with this, and we just go ahead and say that the right half of 3 has been sorted. So we are done with the left half of 3, and we are done with the right half of 3. So we will recursively go back to the parent of 3, which happens to be 2. So once we go back to 2, its left half is done, its right half is also done. So what we do is we go back to 2's parent, which happens to be 5, and once we go to 5, 5's left half is completely done. So the next logical step is we need to go to the right half of 5. So I have just cleaned up everything. So what we are left right now is the right half of 5, which has the elements 8, 9 and 7. So these need to be sorted now. So we have reached them, we have gone back into quicksort and into the main quicksort loop, and we have come out of this particular function for quicksort of 5. So then what we do is we call partition first. So in partition, we assign the pivot to A of L, and in this case it happens to be 8, and then we have to assign I and j. So in this case, I will start at the position L, and j will start at the position R plus 1, which happens to be outside the list. So first step is I increments first, and then we check whether we have hit a condition where A of I is greater than pivot. So since A of I is greater than pivot, we cannot do anything but to stop I from incrementing, and j moves ahead. So first we decrement j, and then we check whether A of j is less than pivot. So is 7 less than pivot? We have actually hit a scenario where A of j is less than pivot, so j also stops decrementing, and then we swap the elements A of I and A of j. So we have swapped 9 and 7, and we have got 7 and 9. Next we check whether we have hit a condition where I is greater than j. Since I is not greater than j, I moves ahead. So I resumes its journey, and I has moved ahead. And then we again check whether A of I, that is 9, is it greater than pivot. So since A of I, which is 9, is greater than pivot, I cannot move ahead, so I stops at this point. Then j resumes its journey by decrementing j minus 1, and we check whether A of j is less than pivot. So since A of j is less than pivot, we are actually done with decrementing j as well. So we go ahead and swap A of 9 and j of j. Though this was not required since the algorithm has this, so we will swap 7 and 9 to get 9 and 7. So once we do that, we check whether we have hit a condition where I has gone ahead of j, and since I has gone ahead of j, we will come out of this loop and again swap back this unnecessary swap that we had done. So 7 and 9 get re-swapped back. After this, the last step would be again swap the pivot element and A of j. So in this case, 8 and 7 needs to be swapped as 7 and 8. So they get swapped, and then the element 8 is in its position. So we will just mark it with our color for positioning, and then we will return the index of 8. So we will return j to indicate that the element 8 is in its position. So I have rewritten the numbers again. So you will see that 8 is in its position, and once 8 is in its position, we go back to the elements. So S contains the index of 8. So quicksort will be called on L to S minus 1. So in this case, L to S minus 1 actually points to the left half of 8, which is just the element 7. So in this case, L is less than R condition fails when we call quicksort on just the element 7. So we will immediately return back from the left half of 8 saying that the element 7 is sorted. So once we are done with that, we go into the right half of 8. So in this case, that happens to be just the element 9. Again, when we go here, L and R point to the same element. So L is less than R fails in this case as well. So we are actually done with the right half of 8, which has just the element 9. So the element 9 is also sorted. So once we are done with 9, so we are done with left and right half of 8. So we will go back to the parent of 8, which happens to be 5. So once we go back to 5, we are actually in the quicksort of 5 and we are coming out of right half of 5. So we are done with the left half of 5 and the right half of 5. So we are done with both parts of 5. So we are actually done with sorting all the elements. So this is the quicksort algorithm and an explanation for quicksort using the numbers that we had used. Now, worst case for quicksort happens to be a scenario where elements are already sorted. So if we have a list of elements that are already sorted, then it is a worst case for it. So the time complexity in this case happens to be theta of n square. So if you see here, the elements are already in sorted order. If we try to sort these elements again, then they will actually take theta of n square. It is fairly straightforward to analyze this, because what will happen is the pivot will start pointing to 1, and then the elements we will compare 1 and 2, and then we see that the element I would be pointing to 2 and j would be pointing to 8, and since 2 is greater than 1, I will stop here and j resumes its journey from here, and it will keep decrementing all the way till it reaches the pivot element, and 1 will be replaced with 1 itself. So 1 would be in its position. Then we go to the element 2, and I would be pointing to 3 and j would be pointing to 8, and I will still remain at this position, and j will again come from all the way till the element 2, and 2 will replace 2 itself, and pivot moves to 3. So what we see is that at every step j has to traverse all the way from right hand side to the left hand side, which causes the complexity to increase, because we are not utilizing the divide and conquer power. So basically what we are doing is a linear search every time for j from right half to the left half. So this increases the complexity to theta of n square. So the average case complexity for quicksort algorithm is theta of n log n. Actually, for this we would have to write the recurrence relation and then solve the recurrence relation to prove that it is of n log n, which is outside the scope right now.